Welcome friends. Today we are going to learn about heat engines from our subject Engineering Thermodynamics. Energy conversion devices. The need is to construct devices which receive heat and convert it into useful work, like in a car engine, or receive work and convert it into heat, like in an air conditioner, in a continuous manner. Thus, heat engine is a device that converts heat into work while operating in a cycle. Heat engines does not produce work because it will be a violation of first law. It only converts one form of energy, that is heat, into other more convenient form of energy, that is work. That's why heat engine is a energy conversion device. Thermal reservoir or heat reservoir. It is an imaginary body with a very large thermal capacity. If some amount of heat is added to or taken from the reservoir, it will not change its temperature. Sea, atmosphere, large lakes or cooling ponds can be assumed as thermal reservoirs. A high temperature heat reservoir from which heat is transferred is called as a heat source. A low temperature heat reservoir to which heat is transferred is sometimes called as a heat sink. Now let us see how a heat engine works. Any heat engine is a cyclic device which receives heat QH from a heat source at constant temperature TH. It converts part of the heat supplied QH into work W net. The remaining heat QL is rejected to a heat sink at constant temperature TL. Note that the temperature of heat addition TH is greater than temperature of heat rejection TL. Also remember that all the heat supplied to the engine cannot be converted into work. Let us find out the energy balance of a heat engine. Apply first law of thermodynamics to the heat engine, which is a cyclic device. So energy input is equal to energy output. QH equal to QL plus W net, or QH minus QL is equal to W net. Thus, work produced by a heat engine is the algebraic sum of heat supplied and heat rejected. Now, let us find the efficiency of heat engine. Efficiency of any device is defined as the ratio of desired output to required input. For a heat engine, thermal efficiency may be defined as the ratio of work produced to the heat supplied. So heat engine efficiency is W net upon QH. Since QH minus QL is equal to W net, as we derived in the energy balance, heat engine efficiency is 1 minus QL by QH. Somebody may ask the question, is it possible to construct a 100% efficient heat engine? For a heat engine, thermal efficiency is defined as 1 minus QL by QH. If the heat rejected to the sink QL becomes 0, the engine will be 100% efficient. In other words, it converts all the heat supplied into work. Unfortunately, this is not possible. By second law of thermodynamics, all the heat supplied can never be converted into work. Some heat remains with the working fluid. To complete the cycle, this heat must be rejected. Otherwise, the working fluid will not be restored to its initial state and the engine will not resume its next cycle. Thus, no engine ever is 100% efficient. To understand the concept of heat engines, let us solve a simple example. Imagine a heat engine receives heat 144 kilowatt and rejects heat 108 kilowatt. What will be its thermal efficiency? From given data, heat supplied QH 144 kilowatt, heat rejected QL 108 kilowatt. We know heat engine efficiency is equal to 1 minus QL by QH. Solve this and you will get efficiency as 0.25. The efficiency of heat engine is always expressed as a percentage. So one can say this engine is 25% efficient. In other words, it converts 25% of the heat supplied to it into useful work and 75% of the heat supplied is rejected. Second example, a steam power plant produces 50 megawatt of net work while burning fuel to produce 150 megawatt of heat energy at a high temperature. Determine the cycle thermal efficiency and the heat rejected by the cycle to the surroundings. Given data is work output 50 megawatt, heat supplied 150 megawatt. By energy balance of heat engine, W is equal to QH minus QL, or heat rejected to sink QL is equal to QH minus W. Solving this, we get QL 100 megawatt. This is our first answer. We know the formula for thermal efficiency, 1 minus QL by QH. By solving this, we get thermal efficiency as 33.33%, which is our second answer. It is found that in practice, actual heat engines offer very small efficiency in the range of 20 to 30%. Now come to the concept of Carnot cycle. French engineer Carnot was the first to introduce the concept of a cyclic device. He proposed a reversible cycle which consists of four reversible processes, namely two isothermal processes and two adiabatic processes. Such a cycle is shown on the PV diagram. The heat addition takes place at a higher temperature, the heat rejection takes place at a lower temperature, and the area of this cycle is the net work output. A Carnot engine, a heat engine that operates on Carnot cycle, is called as a Carnot engine. Since it operates on a reversible cycle, it is also called as a reversible engine. A refrigerator that operates on a reversed Carnot cycle is called as Carnot refrigerator or reversible refrigerator. Since Carnot cycle is reversible, a reversible heat engine can be reversed to operate as a refrigerator. Let us find out the Carnot engine efficiency. Thermal efficiency of any heat engine is 1 minus QL upon QH, where QL is the heat rejected and QH is the heat supplied. But for a reversible cycle, according to second law of thermodynamics, QL upon TL is equal to QH upon TH. We can rearrange this. QL upon QH is equal to TL upon TH. Therefore, Carnot heat engine efficiency can be written as 1 minus TL upon TH, where TH is the temperature of heat addition and TL is the temperature of heat rejection. Carnot theorem. Carnot theorem states that Carnot heat engine has efficiency more than any other actual heat engine operating between same temperature limits. Secondly, Carnot heat engine has efficiency equal to any other reversible heat engine operating between same temperature limits. Note that Carnot cycle efficiency is expressed as a function of temperatures Th and Tm, both are which properties of the system, while QH and QL, that is heat supplied and heat rejected, are non-properties of the system. Let us come back to the example 1. A heat engine receives heat 144 kilowatt and rejects heat 108 kilowatt. What will be its thermal efficiency? For our heat engine, source temperature is 1000 Kelvin and sink temperature is 400 Kelvin. What will be thermal efficiency of Carnot cycle working under same conditions? Compare efficiencies of both engines. As per the previous example, the efficiency of actual heat engine will be 25%. The efficiency of Carnot heat engine as calculated from the temperatures is 60%. This proves that Carnot theorem that a Carnot engine is more efficient than an actual heat engine operating under the same temperature limits. End of the